Good afternoon, everybody. Thank you for being here. This is another edition of our Quantum Research Center seminar. And today I have the pleasure to introduce Professor Jens Eisert from the Freie Universität Berlin in Germany. It's difficult to make a short introduction for someone like Professor Eisert. He's one of the big names in our field. He's a worldwide authority in quantum information, quantum many-body physics, quantum computing theory, computational complexity, and he has done many contributions. He's one of the big seminal players in entanglement theory. He's done lots of works in benchmarking and certifying quantum devices. He's done seminal contributions in game theory. He has written over 100 papers. And so it's really a pleasure to have him here. He did his PhD. He got his PhD from the University of Potsdam under Professor Martin Wilke. His thesis was on entanglement theory in quantum information. Then he spent some time as a postdoc in Imperial College, London, in Caltech, in Pasadena. And then he started his career as professor. He was first junior professor in the University of Potsdam in Germany, then a lecturer in Imperial College again in England, and then finally a full professor in 2008 in University of Potsdam again, and then a full professor in Freie Universität Berlin, where he is now since 2011. Yeah, he has won many awards, including the European Research Council grant, and it's really a pleasure to have him here. He's a big scientist, and also I must say, a great friend. I had the pleasure and privilege of being here being with him as a postdoc some years ago. Now we even have Ingo, who was a PhD student of his. So it's really like part of the family to me. So thank you so much, Jens, for being here and for showing us your work here, being here with us today, okay? So please proceed.
Yeah, thanks so very much indeed. Thanks for this overly and of course, totally unfairly kind introduction and invitation for that matter. It's great to be here, at least virtually in these awkward times, but increasingly less so. So things are opening up slowly, and I think that's a good thing after all. So as Leandro said, I consider this a small family reunion meeting. As Leandro said, he was a postdoc and Marie Curie Fellow in Berlin for some years, in fact, and we had an enormously fun and productive time. There's absolutely no denying. Also, Ingo has just arrived in Abu Dhabi, and we have many joint topics on the desk. So I rather see this as a contribution to getting going with a further and fresh collaboration. I'm very much looking forward to this. Now, there's good news and bad news coming along with this talk. The good news is, as I said, there's a lot of potential to cook up new ideas along the lines mentioned in the talk. The bad news is that Ingo will absolutely learn not anything new from this talk, as most of it will have been done together with him. Also, by my standards, it will not be too sophisticated from a mathematical, pedantic perspective, but rather hands-on, pragmatically motivated. You will see the sweat and oil at work. But for the questions at hand, this can be also a good thing, and that again constitutes good news, I suppose. So anyway, what we have in store today is the data-driven discovery of dynamical laws. That sounds elevated. So what is a discovery? What does a dynamical law mean after all? And what we have in mind here is something very hands-on and basic, and it will remain so for the rest of the talk, unless you press me in the discussion and meditation session. So here's the guiding question. If you can see the next slide. So how can we learn dynamical laws from data? This is not a new question. The Google AI labs in the background may suggest otherwise, and we will come back to this later in the second part of the talk. But this question is basically as old as the endeavor of natural sciences is after all. Think of planetary motion, say. So we do know how this is working, and building on a body of previous observations over the decades and centuries, Kepler did look into the sky in Torun at some point at the beginning of the 17th century and looked at these funny points working around the sky, doing all kinds of funny patterns. There have been lots of explanations before, complicated explanations of those points before, of course, but he sat down and understood that it's a good model that these points are planets that go around in ellipses around the sun. And then he further thought about it and found that there's laws behind that, specifically the squares of the times of these points going around the sun, referred to as planets, would be scaling like the third power of some semi-axis of the ellipse of the ellipse of the movement of the planets going around the sun. Then Newton came around in the late 17th century and found actual dynamical laws in the famous Principia, and reportedly did some reverse engineering to match the observed data with the gravitational force so that it would work out with Kepler's laws, to see that the force in the dynamical law would be giving rise to the Kepler law that was already present and published at the time. So when Kepler looked at the sky, it took many hours of observation, and his genius, and that of Newton for that matter, to find out what the precise dynamical laws of planetary motions were, but they did look at this in this fashion. So such dynamical laws are in the classical realm usually given as guys of that form, like differential operators acting on some trajectories in real variables in one way or the other. And one finds the dynamical laws by integrating up these dynamical laws. So, but how do we know these laws in the first place? Again, finding out this works well for rather simple problems such as planetary motion after all, or systems of the type shown here. That's also still quite plausible. But it's much less obvious if many degrees of freedom come into play. Say in systems biology, where these guys can look as complicated as this or worse. Or in fluid mechanics, say, with like nonlinear equations coming into play in some fashion. There's no hope. We can intuitively understand what's going on. So how can nonlinear laws be learned then from data? And the curse of dimensionality has to set in a serious fashion, again, in one way or the other. Or what's a Hamiltonian? What is the Hamiltonian? That's basically the same question, both in the classical and in the quantum realm. So how can we judge this from data? This also has a fundamental flavor. So in some way, physics is formulated in a way that does not always match reality, or it's like formulated kind of the wrong way around. So when I give a course on classical mechanics, as I fortunately did so for the last time today, that's just the exam running, and or I often do in quantum mechanics, not this term, but the other terms, that it has not been a single time when students did not ask, yeah, but the Hamiltonian governs the dynamics, you say, but where does how do we know the Hamiltonian from? You say it's given and specifying the dynamics, right? But there's no voice speaking to us in the lab giving us the Hamiltonian. Or if there is, oh, well, we might have other problems. So what is the Hamiltonian after all? And that's kind of this data-driven mindset that you accept that data are ultimately all we have, and we have to kind of reverse engineer and see what dynamical laws are compatible with those data that we see. And this will be kind of there was a long introduction, the guiding mindset of this talk. And again, this comes into play when we think of a precise engineering of settings in the quantum technologies, a point that we come back to in quite some detail later in the talk. So how can we take data seriously and learn what's going on behind the scenes when looking at data? That's the outline for the rest of the talk. We look at learning classical dynamical laws from data. Then we look at learning the quantum dynamical laws from data. And then depending on time and your mood, there's an endless procrastination on learning or learnability that I'm happy to say more or less. You can steer me. You have the control, and I will do whatever you like on this. So learning classical laws from data. So here we go. What does it mean to learn classical laws from data? It means that we take data in the first place, we go into some lab and observe what's going on. So we take snapshots of data in time and like estimate right-hand sides of derivatives. And then we see, or we want to know what is the law that's potentially giving rise to those data. And we aim at identifying the governing equations from those very observations that we have done in the lab. How can we identify those potentially nonlinear equations from observations in this kind of data-driven mindset? Well, we can do so by expressing things in something. You have to find a vocabulary of expressing stuff. And we are mostly quantum scientists and think of quantum states. And of course, most of the talk will be on quantum states. But for now, we think of classical laws, classical descriptions, and we have to express right-hand sides in terms of something, some basis functions. And for that, we pick a dictionary of basis functions in which we express things on the right-hand side. Then we construct a transformed data matrix that takes the values that we've done and elaborates them on or evaluates them at these dictionary functions. And then we try to match right-hand sides in the best possible fashion, matching the data that we have. So there's lots of functions and we want to tune the coefficients to match the data. And then we say, we would like to find a coefficient matrix of real coefficients so that the cost function is minimized. And that's a sophisticated way of putting it. I just mean that you make a least square, like Lasso type estimator. So you minimize the Hilbert-Schmidt norm for these coefficient matrices subject to the data at hand to have the best model that captures the data that you have observed in the lab. And if you want to be fanciful, you can add what is called a regularization, so lambda times the one norm to have, say, the Sparse signal that is compatible with the data. And well, that's super simple, admittedly. It works extremely well. It's called SINDI, so sparse identification of nonlinear data, which does find a sparse coefficient matrix. That's kind of Occam's razor at work. The sparsity means that you find the simplest model compatible with the data and say, if you give this guy data from Schur's circuit and see what's going on, then the machine would automatically learn the dynamical law from these data and reliably and stably recover the nonlinear equations of motion from data in just the right way as we want it. So you can learn dynamical laws from data in a reverse engineered fashion. You don't predict or make plots and say, oh, is that kind of working or not kind of working, but you learn the dynamical laws from data themselves. That's great. But how about large systems? How about systems where not 1, 2, 3, but more, many degrees of freedom come into play? Think of these systems in biology of turbulence, where there's lots of degrees of freedom coming into play. Of course, we can no longer just think of arbitrary dictionaries of possible right-hand sides. This will be enormously large, so we have to formulate meaningful, physically motivated hypotheses to even know where to start and then think of ways of recovering stuff from data. But what are well-defined hypotheses of this kind? Well, it takes a moment of thought to realize that if you do a product basis ansatz with many degrees of freedom sitting there, you have a function dictionary per site, a product basis if you want. And then it takes a moment of thought to realize that any function in the span of this product basis can be expressed as a tensor with all the coefficients over these product guys. This is great. It gives a wonderful dictionary, except it's a very large dictionary. It's clearly exponentially large in the system size. And tensor network experts like José Ignacio, they will immediately get the association, say, wait a minute, that's a big tensor. of course, we want to exploit structure in the problem. We know about locality, about locative interactions, correlations. We want to take our scissors out and slice this tensor into pieces and make use of that local structure that just captures the meaningful local correlation pattern that we have. That's a mindset that's extremely common in the study of tensor networks. Of course, that mostly comes from the quantum realm, but for now, let's use this machinery in the classical realm, learning classical dynamic laws from data. So we take our scissors out and cut this tensor into pieces to have a structure of a basis dictionary as a tensor network. This naturally respects locality and natural correlation structures in the problem. For the experts, you will see, wait a minute, that looks like a matrix product state, like a MPS, a many paper state. People like to joke for good reason. And it is, except that it's not a many paper state over quantum states, or nor over classical probability distributions, but over function dictionaries, where each guy labels the physical index monitoring the function dictionary that you have at hand. So this is a tensor network, a network of tensors. So the experts say, yawn, not again. The non-experts will say, what is this? It is a network of tensors. So I've said it. So these dudes, these blobs are tensors. And the degree of the tensor is just manifested by the number of blobs you have sticking out. So a degree 1 tensor, a vector or a dual vector, would be a blob with one leg sticking out. A matrix would be having 2 legs sticking out. A degree 3 tensor has 3 guys sticking out, and so on. And if you connect them, you would sum over the index, so contract this index away. So a cute way of writing a matrix product would be given on the slide here. And again, this MPS, many paper state, this guy would be a tensor network of this type, where you've contracted away the guy in the middle, but equipped with the same mindset and understanding as we love and cherish in our quantum matrix tensor network world, but now over function dictionaries of right-hand sides of nonlinear equations of motion. Again, that's our tensor network for our basis element. That's for basis elements, but that's not all. The same works for sets of functions. And there's also several ways we can incorporate the data tensor into the problem, naturally reflecting the locality and natural correlation structure. One way is to make sure that each tensor core, each blob, each dude inherits an additional index that encodes the corresponding equation. And these additional indices are contracted with a delta tensor, which selects the appropriate tensor core for each equation component. You can also make use of a selection tensor that selects the core that gives rise to a single function, or we can just plain vanilla-ly, is this a word? I don't know. Just append a single extra leg. Sorry, an extra, what's happening here? An extra leg to incorporate the data tensor into the system. So there's many ways, and it should already be clear that each of these representations is efficient, similar to what we know from quantum tensor network land, but it should also be clear that an understanding of the involved rank specifically is key to a good recovery. And understanding this, you see, you go into the lab, you have a kind of data structure, which is the tensor network inspired data structure, and then you can cast this whole problem into a formal recovery problem in a compressed sensing mindset, where you want to minimize, say, the Frobenius norm of your data subject to the coefficients coming from the data structure captured in a tensor network form in this sense. And then all the meat and the hard work starts. I will not go too much into detail here, but you can do all kinds of numerics and prove theorems. For example, a cute insight is that the pseudo inverse that you need to compute things from data can actually be computed with one swipe in the effort given here, going from the left. If the right and the left and the right normal form are nicely made use of in the recovery, because the pseudo-inverse can be basically spelled out in an exact fashion. More practically motivated in either of the mentioned formats, to get a stable recovery, you should better think of clever rank adaptive schemes of running the show. There's several new rank adaptive schemes that have been put forward also in the quantum context of quantum tensor networks. The best performance was done by a scheme called stabilized alternating least square, SALSA, which is a sophisticated rank adaptive scheme of the type that we want and want to see. And this does give rise to an efficient recovery. So to give an example, we have applied this to some model of nonlinear coupled beds and springs, the Fermi-Pastor-Ulam-Tsengu problem, where we have balls and coupled in this fashion, where the dictionary was the first 4 Legendre polynomials per side as an on-site dictionary, lifted up to the full dictionary by the tensor network picture. And then we said, that's our dictionary, let the machine find the dynamical laws from data, just looking at the data. And using these rank adaptive schemes, this works well, and you do find the dynamic laws, the nonlinear dynamic laws from data in this mindset given and mentioned. So lesson, tensor networks give rise to good recovery results. When learning dynamic laws from data, you go into the lab, you don't say, there's some nonlinear equation of motion happening, here's the data, that's my prediction, does it match or not? But rather saying, good, can I take the data, put the data into the center, take them seriously, and then learning the very dynamic laws, the nonlinear dynamical laws from data. And we've seen that a much quantum tensor network inspired approach, I mean, Jose Ignacio will specifically appreciate that, maybe because he has all this background and understanding of tensor networks, you can do similar things on the learning of classical data. Of course, that's only a baby step. Can you say more about hierarchical projective entangled pair tensor networks in that setting, or think of recovery guarantees, expressivities, correlation measures, and much of the intuition that we know from quantum mechanics on Wernier entropies and being able to present states in terms of tensor networks does seem to carry over morally, but not quite mathematically. So there is work to be done on scalably learning dynamic laws from data, but this is a very nice kind of machine learning inspired way of learning, like discovering classical laws from data, if you want, in a purely data-driven fashion. Good. Quantum. I promised not to overrun, so I keep it simple and short.
Could I ask something here, Jens?
Oh yeah, please.
As you cool. So how do you deal with errors then, with measurement errors? So in the simplest case, I could say I have some white noise on my data, so it's not clean. I guess this is somehow incorporated also in your model. Or how would you do this, or how is this done? Well, I mean, it is of course incorporated. I mean, the data are, I mean, these are machine generated data, so they're not real data, but of course they are with errors, and they're simulated error data. And what you ultimately do on the highest level is like a Hilbert-Schmidt norm, Frobenius norm match, given the data structure that you have. So you're basically finding the best representation given noisy data in the two-norm sense. So of course noise is incorporated, and also the picture here does show certain, well, it's a bit abbreviated, but it does show noise. Of course, the data are noisy, and the performance of that recovery will depend on the noise. But the whole point is, of course, that you can learn the laws from data, even if there is noise at hand. Okay, and a more philosophical question, which goes in the same direction. How, let's say I'm an experimentalist, I measure some data, and now let's say I have some systematic errors. Okay, normally I would find those because I compare my data to a model and I see it doesn't systematically fit. Wonderful. But then, yeah, wonderful question. But all the religion and meditation comes at the end. Okay, I delegate this and we come back to this because perfect. Yeah, of course I'm just gaining time, as you might imagine. No, I'm joking. Let's do the meditation at the end because, yeah. Yeah, super. I understand, and this is much less obvious. Learning quantum laws. So you want to learn quantum laws from data. Same mindset. You want to go into a lab now, somebody else's lab. Now it's no longer a biology lab and so on, but it's like this lab here of our friends. This is the lab that we work with, and that we got frantic messages on Friday, like 50 messages, 2 calls on Friday. It was completely crazy on learning quantum laws from data. And then there's many ways of grasping this. Of course, the plain vanilla way of saying this is, what is the Hamiltonian? And again, you say, oh, the Hamiltonian is my guy that describes my system at hand. And of course, that's very meaningful and nice. And we think of quantum simulation or analog quantum simulation, where you say, I have my Hamiltonian prepared in the lab, and then you make predictions going beyond classical simulation methods and all that. And yes, then you say, wait, but is the Hamiltonian that I have in the lab really what I anticipate? And then you can say, yeah, why not? And that's a fair perspective. Also, mildly catching up with René's meditation a bit earlier. So, but if you want to be pedantic, you say, right, but is it really precisely what I think I have? So can I be sure about this? Because if you want to uplift ideas like analog quantum simulation to a new level, that you want to make predictions and see this as a quantum technological device, you better know what your predictions are, because otherwise, how would you make a quantifiable prediction that makes sense to be beyond classical capabilities? Because if you produce random numbers, there's a very cheap way of doing that on a classical computer. So you better know what you're doing on what is the Hamiltonian. It's a very natural problem. So one way of putting it is like a more machine learning inspired way, where you have a Hamiltonian and then you express things in some terms. You pick Hamiltonian terms, a right-hand side, and you have coefficients alpha j you would like to know, but you do not know. You want to learn them. What is hj? That's a matter of choice, and it reflects some a priori knowledge of what's going on here. For example, alpha could be 1 parameter or 2 parameters, and hj are just big chunk Hamiltonians. That's a parameter estimation problem. You have like an easing model. You say, oh, I'm not quite sure about the coupling. You talk to Emanuel Bloch, our friend in Munich. He has some Hubbard type system, and he says, oh, is there some tunneling? That's a parameter estimation problem. Or you say, oh, I don't know anything. Pick an operator basis, and that becomes a Hamiltonian tomography problem when you want to learn the full coefficient matrix of a distribution of terms in terms of an operator basis. That's all included. You have some term given, and you want to learn the parameter alpha. So you want to recover alpha j from time series data taken at snapshots in time in just the way as before, but not in the classical lab, but in the quantum lab, taking snapshots in time up to some tolerance level, epsilon, from time series data. And of course, that's Hamiltonian time. Oh, there's that's what happens when you quickly do slides. There's a sign error in the Schrödinger equation. The right-hand side should not have a minus, but you know what the Schrödinger equation is. It's just Schrödinger dynamics under some family of Hamiltonians, where you prepare fiducial states and you let them run, and then you take a measurement at the end up to some tolerance, epsilon. There's some fine prints of this, and I will not go too much into detail. So that's a Hamiltonian verification problem as a reading there. If you go into the lab, you take data of the type mentioned, and then you say, am I right that the Hamiltonian is what I think it is up to some norm? So do I get the promise that the Hamiltonian that I actually have is a norm close to what I estimate from that to a given norm or not, as a decision problem? That's what we call the Hamiltonian verification problem. Then we can talk about the Hamiltonian identification problem. And that's what we do for the rest of the talk. It's just taking data, and they say, can I learn my Hamiltonian from those data? Really as an estimator of the parameter vectors that, like these alphas in the Hamiltonian, that I want to learn from data, and they say, this is what I have. And then there's the most difficult one, the Hamiltonian dynamics prediction problem, where you just want to say, I want to discover the laws in the sense that I want to make predictions later. This is in the machine learning inspired setting. This is maybe most used, that mindset. It's also not so tricky. It's like you want to learn the prediction itself, but not find the dynamical law giving rise to some prediction. So that's surely meditation level for the religious part of the end of the talk, what it even means to do a Hamiltonian dynamics prediction. I keep it short and I hope not too rushed because I want to have some meditation and religious time at the end. Good, but let's stick to the Hamiltonian identification problem for now. So you have some many-body system given. Think of Immanuel Bloch's code atom systems, or an ion trap system, or a superconducting qubit system of the type that is sitting somewhere. And then you want to learn dynamical laws from data.
And excuse me, Jens, Luigi. Can I ask a short question? HJ, are they commuting?
No, they're not commuting.
Okay.
Not Thanks. In general. No, in particular, even in the simplest meaningful setting, they're not commuting. No, they're never really reasonably commuting. Unless, no, they're not commuting. They're just not commuting. No.
Okay.
No. Yeah.
Thanks.
Okay. This is not so easy. That's obstacles. First, there's this annoyingly exponentially large Hilbert space that we know, and we got over it at some point in our life, but it's still annoying. It's a large Hilbert space. Hilbert space is big. Anyway, then the expression is quadratic in e to the power minus I. Actually, quite literally so in my wrong slide, the one before. But of course, in reality, there should be a plus sign, but never mind. It's a quadratic expression and a non-convex quadratic expression that is also, to add insult to injury, non-linear in H. It's e to the power of something, but not linear. We love linear stuff. We hate non-linear stuff. And that's what makes this innocent problem so tedious and nasty. Let's go over two approaches to tackle this. One pretty briefly and one also briefly, but slightly less briefly. The first one is more machine learning inspired and really following up on the idea earlier on using tensor networks, but now quantum tensor networks to go into the quantum lab and learn in a combination of machine learning, tensor networks, and so on, dynamical laws from data. This is work in progress, but should be done at some point. So where you just accept you cannot faithfully keep track of dynamics from dynamics in the quantum world on a classical computer. It's QMA hard. It's actually BQP hard, as one says. It's a full quantum computer, but you can do so for short times, and there's a machinery of TBD and other variants over matrix product states of the type mentioned earlier, where you could keep track of dynamics for a short time, not very long. That will not work, but for short times at the expense of an exponential effort in the time, but it's a finite time anyway, so you can keep track of dynamics of that time. And then you can think of Hamiltonian parameters fed in. Then you could do TBD time steps, so tensor network time evolution algorithms. You monitor stuff in time, and then you say, is the time part of my time slice I've measured? If no, you continue to evolve. No, until you get a yes. And then you compute out probabilities that are compatible with the data given. And then you get a loss function that could be the negative log likelihood loss function. You compute this, and then you make an automated differentiation framework and update the parameters in the stochastic gradient mindset that updates the parameters to optimize based on the gradient, the negative log likelihood loss function. And that's very simple, and it does work. That's extremely simple. It's this kind of machine learning inspired way. It's a bit annoying how well this works. It's kind of a tensor network inspired approach that does allow to reliably and scalably identify dynamical laws from data, in the sense that you update your parameters in this stochastic gradient sense, and then you can identify Hamiltonian parameters from that setting. There is the data slide missing. I present that later. So when I did this, I have a slide from the convergence shown, but then I say it in words that it very quickly converges. And the picture I said was from an XYZ Hamiltonian. So there's some free parameters in the problem, and you feed the system some data. It's a full many-body problem. It's a non-integrable many-body problem because you break integrability. It's not so easy, but you can evolve stuff for short times. And then you see what's happening in time, and then you do this loss function optimization, and then you see that it nicely converges and finds reliably the coefficients that best match the data, and then you can, in the full many-body regime, identify dynamical laws from data in the sense also for non-integrable models in a truly scalable fashion, overcoming the curse of dimensionality, because you do not need to keep track of the evolution for all times, which you cannot, but you don't need an efficient representation of any of the dynamics, which you can't, but you can do for relative short times for tensor networks, and combining tensor networks, a machine learning inspired way, and this automated differentiation machinery, you can reliably learn and scalably identify Hamiltonians from data, overcoming each of the mentioned points. It's scalable, you overcome the problem of nonlinearity, and you get reliable data. I'm happy to show this slide so that went elsewhere, but it just shows you what I've said in
Jens, can I ask you, interrupt you, one question? So about the operational procedure in this type of experiment.
Yeah.
So you prepare an initial state and let the Hamiltonian evolve. Yeah. And then make a measurement, and you do the same thing for different times of the evolution, or you also kind of make a measurement and then use that state after the measurement as the initial state of the following step. How is the protocol more or less? Like,
so I only have one point in the entire talk. It's of course we go long and winding. It's many ramifications of the same. It's always fixed. You fix parameters, you evolve them in time, and then look at it, and then you learn something about this. But it's not that you along the way update and try to do for later times. No. You fix parameters, you let it go, and then you say, is that compatible with my data? And then you learn what's going on based on that. So it's Fouquet and not Brownian in this.
All right. Okay.
All through the talk, there's no modification. That also applies to what I will say in a second, when you say, can such methods be made waterproof experiments? Because then trouble starts. Now I was talking about tensor networks, machine learning, non-integrable models, and whatnot. And then I say, can such methods be made waterproof experiments with noisy data in a spam robust fashion? And then I will backtrack and talk about an idiotically simple class of models. Well, Ingo will be annoyed when I say this. I'm just saying this in a forward-looking way, in that when you really want to talk to experimentalists and be ready to think of state preparation and measurement problems, of noise along the way, of other uncertainties, you better understand what's going on, even in the simplest of all settings, to move on from there. And it was a long and winding story to make such methods waterproof for experiments. In fact, for a very simple class of models, non-interacting bosonic models, where we collaborate with Google AI on superconducting devices for the concept class, family of Hamiltonians, of just non-interacting Hamiltonians, bosonic Hamiltonians, or equally well, the one particle sector of interacting Bose-Haber type systems. That equally makes sense because the one particle sector is uncoupled to the rest. You just want to learn the one particle sector of a bosonic Hamiltonian. Then you say, you must be joking. How difficult can that be? It's just the Hamiltonian matrix is an n by n matrix for n degrees of freedom, and not 2 to the power of m. So the curse of dimensionality is already inbuilt, because you want to learn an n by n matrix and not something to the power of n. What is more, operators transform linearly, which means that you can even spell out the mode decomposition, and the Hilbert space transformation would be the metaplectic representation there if you want. So it's just if you prepare single excitations and wait, you can even spell out in terms of a matrix exponential of this Hamiltonian coupling matrix what the entries would be when you measure canonical conjugates, canonical coordinates later at snapshots in time. As Landry says, again, fixed guy, you evolve it in time in the same sense, but now measuring excitations in the qubit system. Oh, qubit, now I'm saying this myself. I always criticize Pedram for saying qubit system, because it's a bosonic system, but of course that in this microwave setting, this jargon makes perfect sense. Anyway, it's a bit jargon. Anyway, I have single excitations and I have this. So you can even basically access the full transformation method, the unitary, but acting in mode space, not in Hilbert space. So that ticks number 2. It's still painful. I mean, ask Ingo about this. And you see my wonderful hair over this. So what we did was a 2-step approach. on the highest level, you go into the lab, you take data, and then you learn frequencies, and then you learn eigenspaces. Any operator, in particular if it's Hermitian, is governed by the eigenvalues, and by the eigenvectors, and that's what we're going to do. We learn the eigenvalues, the frequencies, and then we do an eigenspace reconstruction, and from that we learn what's going on as a dynamical law from data. Now the devil is in the detail, and it's pretty tedious and long and winding to make progress. Again, the data are, you excite a single guy, you let it run with this non-interacting plain vanilla Hamiltonian, and you measure it. And these data are given here, I mentioned that, except that there's a further matrix S here that I add because we want arbitrary linear maps here that capture state preparation and errors. There's a ramp at the beginning from the experimental context that's not fully under control. And there's also couplers that match to the interacting values. So you want to have a spam robust setting, so state preparation and measurement, or spam robust, actually, let's not go there, like a state preparation and measurement robust scheme that has a freedom of an additional linear map that governs all the stuff you don't like to see as a ramp and measurement stuff and so on. Then there's the Hamiltonian. That's the sum of terms with eigenvalues and eigenvectors. So that's great. So the signal is very simple. It's a linear superposition of sinoids. Unfortunately, it's not good enough to just understand the frequencies. That's how we came into play in the first place, because Google took the data, made a discrete Fourier transform, and said, oh, it's not really working out. Why is this? And they got very confused, and then they contacted us, and that's how this whole collaboration started many months and years from now. And then we understood, wait, it's not good enough. It's the pixeling of the discrete Fourier transform would not be accurate enough. You have to do better and go beyond Nyquist resolution in this setting to then get a reliable recovery of the eigenvectors. You have to go beyond the standard resolution limits. And then understanding that the signal is sparse, you just have a couple of frequencies, you can denoise the signal and achieve super resolution beyond the Nyquist limit using ideas of Esprit and other super resolution techniques to overcome the pixel limit of the resolution limit in like this Shannon-Nyquist resolution limit. So find the frequencies. So in practice, what we did is we achieved the optimal robust by superimposing signals in the right way so that the peaks are just aligned with respect to each other, and then found the eigenfrequencies using super resolution methods like music or Esprit, which set up Hamiltonian matrices and identify the dominant dimensional subspace in the range to get a resolution that's better than the Nyquist resolution, and identifies the frequency in a robust and at the same time super resolution type fashion. So we have the frequencies. And then find the eigenvectors, which means you have to go into the setting and find an orthogonal matrix that gives rise to the basis transform that's happening. And that's again a bit tedious because you can, you can spell out the problem. You can write down the identification of the eigenvectors as a quadratic optimization problem, because it's just a least square thing of taking the data and then, given the frequencies that you've already obtained, match the eigenspaces. But then you have further the constraint of orthogonality and the support constraint, which are quadratic but not convex quadratic. So this is a quadratic optimization problem subject to annoying non-vex constraints from orthogonality, but this can be solved with manifold optimization over ON, which is just a fanciful way of saying that we have to adapt the right basis, find the right basis that matches the data at hand. And this does work. You find the frequencies, you find the eigenvectors, and then you get an estimate of H bar. And you can do so by absorbing S. You recover S, you recover the Hamiltonian, and also recover S, this free matrix in the middle that would absorb the ramps and the stuff you would not like to see. And you don't want to have. That's matching all the dirty stuff in the experiment. That is a robust way of learning the Hamiltonian from these noisy data. And it works well. It works nicely well. So we, as I said earlier, we've joined forces with our friends at Google AI, and they took data, and it was a very intense collaboration over the months and years with some slow phases. As I said, last week was completely frantic with 2 calls a day and lots of communication, where this picture here, for example, shows 5-qubit data as a time series, as basically the raw data. And below you find the Hamiltonian matrices as the anticipated matrix and the estimated matrix and the deviation from the estimated data that really recovers what's in the lab and to what extent you get a deviation from the Hamiltonian compared to the anticipated Hamiltonian that they think they have, but they don't quite have. And this is a recovery with unprecedented description, efficiency, and also accuracy in recovery, but also at the same time an experiment to unprecedented precision, because now one can really recover what's going on in the lab. This is a particularly cute picture because that really maps out the Sycamore chip, where Pedram has been walking around the chip and identified the parts in the setting where one can really see what parts are better and how the quality levels are in a spatially resolved fashion. There were even like funny things happening. At some points, the Z basis was flipping. There were spin flips where the spin up was actually spin down. You can't make that up. Like Google world domination, the world domination team sometimes has the Pauli's flipped, well, what you wouldn't see in the random circuits, which was then found using these identification techniques, because you can really look what's going on, and then you see what's going on in a precise and reliable fashion, learning stuff from data. So these are steps towards an ultra-precise analog quantum simulation. It's nice because you go into the lab, you take data, and you learn stuff, but I mean, it's good what you see. It's also very precise, but it's even better that you know even more precisely what's going on in the lab, because then you can get like actionable advice and see how you need to improve things, what the bad qubits are. There's always the second referee, that's the bad guy. We have qubit 4, that's the bad qubit. You want to know, and using these techniques, you can know and to know what's going on. 45 minutes into the talk, I'm basically at the end. I take maybe 50 minutes, and then we have 10 minutes for religious meditation, if that's good. So I would kind of say stir up at the meditation by somewhat superficially going over a couple of points, if I may. But this will be superficial, but ask me if you want to hear more about this in this meditation outlook. I'm happy to say more, because I wanted to keep it crisp and having a single message in this talk. So in this talk, we look at dynamical laws as they can be scalably recovered from data. In the classical realm, we wanted to learn right-hand sides of nonlinear equations of motion, where we understood it's all about the hypotheses, it's the data structure, stupid. So tensor networks allow to recover nonlinear classical laws from data in a very much quantum many-body sense, except applied to classical dynamical laws from data. And then we moved on to a robust recovery of quantum Hamiltonians, briefly in a machine learning sense, but also a lot in the Google AI-inspired non-interacting bosonic setting, which is very simple physically, but where all the brute force of noise, of spam robustness comes into play and makes our days short to have tools that live up to the expectations of an experimental recovery, which is much dirtier than one might have hoped for. This was the talk as we have it. So of course, there is more you want to see and understand. We are just thinking about higher particle numbers. For now, it was just low particle numbers. What can you do? We have think of analog randomized benchmarking. Can you use ideas of randomized benchmarking to bring them to the analog world? That's a tool that's much needed in the analog quantum simulation setting, going beyond learning, but rather as a benchmarking in a spam robust fashion of analog devices.
We just put out a comprehensive mother of randomized benchmarking schemes. That's a kind of a mathematical mother of all possible randomized benchmarking themes. I'm happy to say more about this, but press me if you want to know. Classical shadows, robust classical shadows. It's also one of the ingredients in our vision, like more long-term vision, to take steps towards a rigorous quantum system identification of really seeing what's in the data and how much you can say from realistic data on practical experiments at hand. Oh, one paper I do not talk about. Let me keep this for the question session on quantum learning, on a proven exponential separation of our quantum over classical circuits, meditating on what it even means to do quantum learning. I'm happy to say more, but I don't want to overrun. But that's maybe the result I'm most excited about that we obtained in the last year. In the classical world, you want to get more recovery guarantees. You want to know what's going on in the lab. Can you say that you really have what you think you have? There is interesting complexity theoretic obstructions that can come into play, in the sense you take data and you ask, is there a dynamical law compatible with it? But it can be that this very finding of dynamical laws can be hard. It can be computationally hard. There's NP-hard problems of meaningful questions of recovery in the quantum and classical world. I just jump over this, but if interested, ask me about this in the meditation session. So this brings me to the end of my talk. So in this talk, we looked at learning dynamical laws from data in the classical and the quantum realm, and we took two very nice baby steps in a good direction. They were scalable. Yes, they were robust, in particular in the quantum realm, because we took data and saw what's going on. But there's limits. You can ask questions what it means to learn, what is there, what are obstructions of a signal processing type, but also of a complexity theoretic type. What is in the data and what is ultimately learnable from data? And these are practical questions. These are conceptual questions. And I would like to invite you to think more about these questions, and let's maybe meditate on them together. And with this, I would like to thank you very much for your attention. I'm looking forward to the questions you might possibly have. Thanks for your attention.
Thank you so much, Jens. Thank you so much and congratulations for the wonderful results. And this has been a very interesting talk. Thank you also for staying punctual with the time. This is great.
This is my German side.
this is great. This is great. I have some questions. I don't know if somebody else wants to start before me. If somebody.
I have one question.
Luigi. Yeah, please go ahead.
Yes. Jens, thanks for this beautiful talk, first of all. I'm sure you know that long history, how to reconstruct the Hamiltonian out of the scattering data.
Yes.
So
you mean like in nuclear physics?
In nuclear physics, or if you want, I mean, in condensed matter, we use the thing to construct the integrable system looking at the scattering matrices, right?
Mm-hmm.
So you formulate the thing and you formulate the Baxter equation, and then you go back to the Hamiltonian. So is it somehow your approach related to that, or?
This is an interesting question. Actually, it's interesting in many ways. One way being that I heard many questions in that context, but it's the first time I hear about Young-Baxter and S matrices. Of course, you're right. I mean, much of the efforts in like nuclear physics and so on were concerned with, I mean, you say it, Young-Baxter type, like integrability type, where you're basically using the S matrix, you would infer about some underlying Hamiltonian description. I would say this is technically very different and very much in similar mindset, except that the figures of merit are somewhat different and the guiding principles are somewhat different. So in the mindset of our talk today, scalability is much more in the focus. So there was this kind of religious thread through the entire talk that I always wanted to go big, want to think of many degrees of freedom in the classical world, but also in the quantum world, and the techniques you mentioned on S matrices and so on.
they're necessarily confined to very small dimensional systems. The inversion is very tricky and ill-conditioned and so on. It's not really a scalable method and doesn't have to be, because it's like finite sized systems. You think of nuclei and whatnot. But what we have in mind here is go big, go scalable. Think of many degrees of freedom in the classical world, but also when you think of quantum simulators, think of big systems, mainly degrees of freedom. So I think morally, yes. The new take is that we are more interested in scalable machineries and take also noise more seriously, because that's much more of an issue when you want to deal with data. And an aspect that I didn't emphasize so much today for reasons of time, but I would have loved to, is that nowadays you take a more kind of rigorous mindset that you want to recover, but also get recovery guarantees and say, this is what I have, but I'm sure up to that level of certainty that is like that. So yes, it's related, but no, there's kind of new twists coming into play. I think it's fair to say.
Okay, thanks. Thanks a lot.
Does anybody else has a question? Have a question? If not, I can. Jose Ignacio. Yeah, please go ahead.
Yeah, it's more on the philosophical side. Yeah, when Jens and I met in the beginning, and Tensor networks came up. Many of us were investigating these ideas, and actually, with Sofiane Iblisir, we wrote a paper in 2007 or around, where we took this idea of having these continuous functions attached to Tensor network, and we applied with quite a number of things. In particular, one of them was solving differential equations. So actually, it's a very nice technology. So what shocked me then, because I was working on my particle physics life on neural networks, was that suddenly I had two ways of addressing this learning of functionalities. One was neural networks, and the other were tensor networks, properly adapted to the continuous. And my take at that time was that essentially the good thing about tensor networks were that they incorporate symmetries in a very nice way. So, locality or scale invariance, whereas the neural networks was not, there was no way, to me, the clear way to do these things. On the other hand, the redundancy of neural networks and the techniques to train them were also really very spectacular. Huh? So I always had this feeling, a very peculiar feeling, that we had two techniques, and it was more, I felt that many people were defending one or the other more as a basis that this belongs to your field, that to be honest. So in this way, my philosophical question is, what is your fully honest comparison between using this kind of techniques, the ones you presented in the first part of your talk, and neural networks, properly trained and good neural networks, not superficial ones?
Wow, wonderful questions. I mean, it's like more an agglomerate of questions, right? It's more than one, and it's like an entire picture you're painting. And I have a lot to say about this, but for reasons of time, I will keep it short, but I'm happy to say more. A couple of things come to my mind. I maybe go chronologically to what spiked to my mind. First, I'm much aware of your beautiful paper. In fact, I defended this recently in the Tensor Network seminar where people talked about continuous dictionaries. I said, wait a minute, there was this paper by Jose Ignacio and Sofiane and so on that. And we were all fighting at the time to get good basis functions for continuous variable quantum systems. And there were ups and downs and some good news and also numerical problems. We all know this. That is wonderful. I mean, I'm also aware of your work on the differential equation. That's much similar in mindset and very, very much along these lines. But then your bigger question was neural networks versus tensor networks. And as you must know, I mean, I like to work in more than one field, and I'm really very much against political and philosophical boundaries between fields. I find it awkward when numerical people hate mathematicians or mathematicians laugh about intuitive people or whatnot. So I'm much aware of these fights between tensor network people and neural network people. This is really, I don't know, we should be beyond that in the meantime. Because as you say, there are many similarities,
between tensor networks and neural networks, which is also more than a superficial resemblance. But they're not the same. I mean, neural networks have nonlinearities. Tensor networks are linear by construction, but they are more related than one might think sometimes. For example, there is new papers on the expressivity of neural networks expressing them as tensor networks, so using them as a mathematical tool to say, wait, we understand the mathematics of tensor networks, to then go back to the neural networks and learn something for them. Or there's also tensor network-inspired approaches in machine learning that sometimes outperform neural network-based approaches. So the fields are moving together, and I think that's a good thing, and I'm quite excited about this. You say symmetries, yes, that's much easier in tensor network land. There I really know spot on what's going on. In neural networks, one can also incorporate them, but I would be much less knowledgeable of how this would precisely work, and it's less understood. I think your bigger question was, what's my feeling? And I think is one should be unpolitical about this and take the best of all worlds. And it, for example, as we did on the topic that I just briefly mentioned on using machine learning inspired approaches to keep track of Hamiltonian dynamics, where the nice two worlds come together. And also it really depends on what you want to know and learn. There was nice work by Renato Renner and others who said they want to discover laws by making predictions, by having predictive power on stuff. You take an apple and you say, what's happening to the apple 2 seconds from now? And then Newton says, it's on the ground. And then the machine learns it and it says, it's on the ground. And that's great. When you really want to learn like directly the prediction, then neural networks are much better. But you want to learn the right-hand side, tensor networks are better, as we show. But then using the tensor networks, you can make long-time predictions. You can say, what's the physics going on? You get explanatory power into what's going on. That's something neural networks cannot do. I mean, you never know what they learn. If you give them pictures of horses, they learn horses, but then you think about what they're learning, and then you realize that they're actually learning the copyright logo on the left, right corner, because horses seem to come together with copyright logos, and then for legal reasons, and the machine learns the copyright logo. So stupid jokes aside, that has less predictive power on the law itself, but often better power on saying what's happening at the right time. So my higher level answer is, be unpolitical about this, know both sides, and just use the best of both worlds and combine them in the right fashion.
Nice.
Thank you. I have a, thank you very much, Jens, and I share fully your opinions. A very, very short question. There was a transparency about the Sycamore test.
Yeah.
But the Q3, Q4, Q5.
Yeah.
What is the Q3? What is the meaning of that?
Oh, these guys. These are the qubits.
The next one. The next one.
Oh, yeah.
Yeah. What do you mean by NQ3, NQ4, NQ5?
Oh, these are the from 3 qubit data, 4 qubit data, and 5 qubit data assessed from that.
But then the quality of each individual qubit depends on that, because some are blue and some are yellow in the different things. So is the qubit not working equally on these different experiments? So this is a lack of consistency then. You're not learning the law. You're not learning the law of the Hamiltonian. You're learning that the qubit has a randomness there.
This is...
Look at the top on
yeah, this is right. This is
yellow
right.
to blue. So depending on whether he's involved with 3, 4, or 5 qubits, it changes its quality?
This is right. Yeah, okay. There's something to be said about this. Yeah, Ingo, do you have a view on this?
So wait, because we may need to give him, I need to give him permission to speak. Hold on. Hello to talk. Yeah. If you want to say something, Ingo, you can talk. I don't know if you...
That's okay. You know, it's a question that it's deep in my mind. To what extent, when you measure things, it's related to what René said, how you deal with data which carry errors. So you have to be very careful in how you infer information about the Hamiltonian, because the data may be inconsistent, and therefore you're learning noise. And that has to be done very, very carefully. You know, I'm talking about my experience in high energy physics and phenomenology with neural networks, and learning statistical errors, systematic errors, and normalization errors, which are the three that appear over there, is a highly non-trivial problem. Highly.
Yeah, indeed. Let me comment on this. So indeed, that's right. And that was also mentioned earlier by René, and now we are basically wrapping up also his question, in that also the question he actually did pose, like as you seem to say, and I fully agree, that statistical errors are always easier to deal with than systematic errors, right? Because that's just statistics, and also in the way that I mentioned at the beginning on the learning classical laws from data. Of course, these are noisy data, and you can still reliably learn them. Also on the quantum side, you can it's all about robust recovery, which is robust in more than one way. It's robust against noise, like of a statistical sense. But there's also other sources of errors. And then there is certain types of systematic errors that you can deal with and that you can incorporate in kind of modeling, and those that are conceptually more tedious. So in our model, we had this matrix S, as you remember, that's kind of incorporating errors of the type of a ramping up. So there's a kind of an initial process of some type that would not be arising from a Hamiltonian with fixed parameters, but something else that would depend on a time-dependent Hamiltonian and so on. There's also a measurement matrix M that I didn't talk about at all, but this is there and can be incorporated in the sense that you have like further free parameters that you basically get out, and you say, wait, how can you get this out? But then you realize that, say, this matrix S is like one size fits all for all time slices, and the very independence of time makes it work that you can recover H and S at the same time. So in this sense, there's systematic errors, if you want to call that systematic errors, that you can incorporate and recover from data in a reliable and faithful and nice fashion. Yeah. And also in the in the Hamiltonian learning sense, I mean, you have like some parameters, and then you, if there are systematic errors, you would basically learn a model that would be faithful to your systematic errors, because you are just learning what you actually have and not what you think you have. And then when you systematically get an offset that's different from what you think you have, that's a systematic error, but that's precisely what you're learning. So in this sense, you're safe because you will reliably learn what you have in the lab from data. It becomes less obvious when you kind of go outside the concept class that you're considering. Say you have something completely different. Like Google just published a paper on catastrophic impact of where like particles from outer space come into the chip and just destroy everything. That's apparently a problem because it destroys coherence, and then you are completely off. That's not inside your model. That's a kind of systematic error of a catastrophic type. But there's also other things that are outside the concept class you're considering, but are not as catastrophic. And then you need to start thinking, and then there's also philosophical question coming into play, like what is a meaningful way of doing model selection, of arguing about how many parameters you need and what a good concept class after all is that can capture your data. And there's something to be said, I mean, that relates to notions of generalization and so on in machine learning, and there's a machinery known, but overall, I think it's a good idea to be alert that the model you are trying to match might not be good enough and might not be predictive enough to capture your data. So my advice is be alert, I mean, as Jose Ignacio already is, and be open, because one has to be aware that systematic errors outside your Hamiltonian concept class might come into play.